Hi, this is Mark Barkey at the University of Alabama. In this video, I'm going to continue on talking about rainflow cycle counting. In particular, we're going to end up developing an algorithm for rainflow cycle counting. But we're also going to talk about variable amplitude block cycle loading for fatigue analysis and peak picking and rearranging the history to start and end with the highest point. So to give a little bit of motivation for this, if you were to work at an automotive company, and many years ago I worked at General Motors, you would have maybe a strain history, or it could be a load history, or you can think of a time or stress history versus time. And you'd have a variable amplitude history that would be generated by taking an instrumented vehicle over a test track. The test track could be a rough road, it could be a pothole, it could be any number of different types of test track that they have at the proving grounds. But these time histories are very distinctive. So for example, if you go over a pothole and you have maybe the suspension component instrumented, what you would see would be you'd have some initial level of noise. You'd have a little bitty ups and downs, and then you would enter the pothole maybe with the front tire, and maybe you would see a little bit of increase in strain or stress, and then the front tire would go through it, and then the back tire, which is maybe the one that's instrumented, would go through it, and so you'd see a big spike in load, and then things would kind of damp out, and you have lots of different ups and downs through here. And then you might have some permanent deformation, or maybe it goes back to its original level, and then you get back to this kind of noise level again. So that would be a typical time history. Again, they're fairly distinctive. A pothole is going to be a lot different than a rough road time history. But with modern data acquisition systems, what happens is that you don't just have a few points in this. Maybe you're sampling at a data acquisition rate that's in the kilohertz. So you have thousands of samples per second, and this event may take 10 seconds. So you have a ton of data, and somehow you need to do a fatigue analysis. Now this data is not only used for fatigue analysis, but it may be used for suspension dynamics or some other vehicle handling group. So the data acquisition group not only takes your data for fatigue, but they take the data for all these other groups, so they need to make it as robust as they can. So you end up usually with a ton more data than you actually need. So let me put a few points in here just to represent what we might see. Of course, all these little ups and downs are points. We have a whole bunch of them in here. We got a whole bunch that come along here. We have a whole bunch of data that goes here. All these different red dots are different data points that are taken at our very high sampling frequency. But this is way more than what we really need for fatigue analysis. The other thing that we need to understand about fatigue is that it's cyclic loading. It's not only cyclic in the sense of this particular event, but it's cyclic in the sense that you don't just run over one pothole in the life of a car. You run over pothole after pothole after pothole in the life of a car. So really this event that we see right here, we can take that entire thing and we can copy it over to this spot. Maybe I can even do that on the screen. And what we have are a series of blocks of this loading history that repeat one after another. Now, from the fatigue analysis perspective, it doesn't really matter if we start at this point and say we have 3 repeats, or if we start at the highest point and start and end here and say we have a repeat. So what we're going to do is we're going to start and we're going to end at the highest point in our variable amplitude history. We're going to call this our variable amplitude block. Okay, so it goes from here to here. Now there is a reason why we want to start and end with our highest point in our time history, and that's to make sure that we have every single hysteresis loop close in our rainflow cycle counting algorithm. If we don't start and end with the highest point, or we can do the lowest point if you want, if we don't start and stop with our extreme value. Then what we have are a bunch of unclosed hysteresis loops at the end, and those can be a little bit of a pain to deal with. Now there are ways to deal with them, and we'll talk about that probably in the last video in this sequence. But for now, we're just going to wrap this time history around so that it starts and ends with the highest peak. So that means if I were to give you, and I often do this, I often give my students a variable amplitude loading history. First thing you're going to need to do is you're going to locate the maximum value in that time history, and then you're going to take everything that precedes it and put it back at the tail, and you're going to start and end with this highest peak. So now we have it from here to here. Now the other thing that we need to understand then is that we really only want the peaks and the valleys in our time history. We need to understand how to reduce that data so that we only get peaks and valleys. Okay, this is called peak picking. Let's see if I can, let me try this color. We know that this point and this point are the ones we want to keep in our time history, and all these other points I want to get rid of, and like this point, and this one, and this one. This will do a few things for us. This will really reduce the amount of data that I have to collect and keep. And it's also essential for the algorithm that we're going to develop. All these little bitty ones in here are kind of annoying, but we'll have those in here. Talk about how to get rid of very small amplitude, non-damaging noise events later. But those are the points that we'll want to keep for our time history. So let's see if we can resketch this. So we're going to start up here. I'll do a few of these. I think I'm on track here. Not completely lined up in time. And then we get up here, we have a bunch of this little bitty stuff. I'll just do a few like that, and then we go up to this one, go down to that one, and we go up to that one. Okay, well, in order to identify whether or not we have a peak or a valley, probably the easiest thing to do is to look at 3 points and determine if the slope between the 2 consecutive points are the same sign or the opposite sign. Let's talk about peak picking. Alright, so we have our strain history or our stress history or whatever we want, load history, and we're going to take a look at peak picking. And this blue line represents kind of a connected line that connects all these different discrete points that we have from our digitized data history. It's very easy these days, as I mentioned, to hook up data acquisition systems. It wasn't always so easy. Used to be, and I've done this, we'd have to record data on VHS cassette tapes, magnetic tape. We'd have to take those magnetic tape, it's an analog system, and play them through a digitizer and digitize those. And then after they're digitized, then we can do our calculations with it. Modern data acquisition systems can digitize very quickly and on the fly. But you have all this data. I have here 11 data points. And all we really want, as I mentioned, the peaks. We want to end up with only this point and this point. Maybe this one down here is the lowest. Maybe this one right here. So what we can do is we can take a look on this curve between point 1 and 2 and point 2 and 3. Now I'm assuming we have a constant data acquisition rate, so our delta t is the same. So here we have the sigma, and then this way is our delta t. That's our time. And delta t is a constant spacing in between. So we have a slope from 1 to 2. Okay, so that's going to be the rise over the run. So it's going to be point number 2, the value of that minus the value of point number 1 divided by delta t. Now, if delta t is the same for every increment, we can get away with not even worrying about dividing it by delta t. But then we have the slope from point 2 to 3. Okay, so we can go and we can take point 2 or point 3 minus point 2 divided by delta t. And then we can see that if the slopes have the same sign, then we have not identified a peak. But if the slopes have different signs, like 6 to 7 and 7 to 8, if those slopes have different signs, then we do have a peak. It's in the middle. So let's write it this way. If slopes have different signs, then we have a peak or valley. And so we can process our entire time history this way, and we're left with just our peaks and valleys. We want to do this for this next step. It's not only a data reduction technique, but it is necessary that we do these things. So we need to do two things. We need to start and end our time history with our maximum value, and we want to only have peaks and valleys, consecutive peaks and valleys in our time history. If we don't, it's going to mess up our algorithm that we're going to develop for rainflow cycle counting. Alright, so let's develop our cycle counting algorithm. So we have a peak picked and rearranged time history at this point. And we talked about hysteresis loops. And in the context of hysteresis loops, there are only three things that can happen to three consecutive points in a time history. So let's do this. Consider three consecutive points in a time history. And I'm going to call them A, B, and C. The first thing that can happen is that the range from A to B is exactly equal to the range from B to C. And what would happen on our hysteresis plot, again we're somewhere in the middle of this calculation in general, would be we'd have a plot that looks like this, where we have A, B, and C. We have a closed loop. And it has a range of A to B, and we can also calculate the mean if we identify A and B. I like to call this one case 1. Now we could include this into this next case, and that's the case where we have A, B, and C. Now I'm showing this positive to a higher value to a lower value. Could be the other way around. It could be a low to a high to another low value. But if we have this case where we have A, B, and C, and these, in this case, we would be starting at point A, we would coming down to point B, and we would close that loop, but we would continue on a little bit extra. So this would be A, this would be B, and we would have point C all the way over to here. And in this case, we have a closed loop from A to B again. We've identified that, but it has a little bit extra, so we're going to have to deal with that later. And this one I like to call case 2. All right, now the third case would be we have A to B to C. When I talk about these ranges, I'm really talking about absolute values. So in this case, A, B, if we do it this way, would be less than BC. Or we can say BC is greater than AB. Maybe that's a better way to do that. And in this case, we would have BC, the range, less than the range AB. And let's see what that would look like. We would be here at A, we would come down to B, and we don't get as far as A again, but we have stopped right here. So this would be no closed loop. And this is what I would call case 3. Now what happens next depends on how big the next point is. If we have a fourth point, point D, well, in the case 2, point D would have to be a decrease because we have consecutive peaks and valleys. If we have a peak one time, we're going to have a valley the next. So if point C is a peak, point D must be a valley that comes down here. So it may end up being one of these cases again. We can go all the way down to here, or we could have somewhere that's something that stops part way down. Point D, now it isn't going to continue on as another increase, but point D is going to have to be down here, and it's either going to be a case 1, a case 2, or a case 3. So let me dot that in. Let me make this on a new page, I guess. So here I'll put it in the corner of this page. So if we had a point D after we follow up with a case 3, point D is going to have to be a valley, so it's going to be a decrease. It could be right to here, in which case we go back and have another case 1. It could be extending down this way, in which case we would have a case 2, or maybe it stopped at this point and we'd have another case 3. What we do after these cases have been identified forms the basis of our rainflow cycle counting algorithm, and sometimes we keep a point and put it in storage. Sometimes we retrieve a point to look at the next point in the time history and so forth. And I'm going to try to help you develop that algorithm. But really, at this point, with this introduction, I would hope that at least the students in my class should take the effort to try to develop the algorithm themselves and understand how this rainflow cycle counting works. If you can write a program that does rainflow cycle counting, then I know that you understand hysteresis and material memory, at least in the uniaxial sense. Alright, so let's work our way through a couple of time histories, and we'll identify our case 1, 2, and 3 that we just talked about. And we'll also see how we identify the cycles. We'll kind of check to make sure things are working out. And then it'll also help us identify what we need to do next to flesh out our algorithm. Right, so here is a stress versus time history. I have my stress points here, and again, I only have peaks and valleys in this time history. That's all we need. Let's go ahead and sketch the hysteresis response so we kind of know what we're looking for. So monotonic up to 500, go down to minus 200. We have a little bitty loop here. We go back to minus 200 again. We're going to increase to positive 200. We go down to minus 50. And then we go up here. From here to here, that's a loop, and then we complete the branch to make a loop, minus 500, minus 200, and 500. Okay. So in the end, we should identify ourselves having 3 closed hysteresis loops. Let's check our algorithm. And again, like we did before, we're going to make things a little more complicated and everything. So let's call this point A, B, and C. Let me use a different color. And the first thing we're going to do is we're going to read in those 3 points into our computer program. And we're going to calculate the range AB and the range BC. To simplify this a little bit, I'm just going to go like this and call that the range AB, and we're going to compare that to the range from, that's range BC, we're going to compare that to the range AB. Now in this case, range AB is less than the range of A. The range BC is less than range AB. This is our case 3, no closed loop. So now what we're going to do is, if we don't have a closed loop, we're going to read in this next point. But instead of calling that point D, I always want to work on points A, B, and C. So what I'm going to do is I'm going to say, I know I have that point A. I need to store that point A. I need to remember it. So I need to keep track of how many points I have in memory as well. So I'm going to say, let's say memory is equal to memory plus 1, where in the beginning I had memory equal to 0. Okay, and then what I'm going to do is I'm going to remap these points. My new point, I'm going to store point A. So store mem is equal to the value for point A. My new point A is going to be equal to my old point B value. My new point B value is going to be equal to my old point C value. And I'm going to read a new point C out of my file or my array. So let's show that mapping. Okay, so this went to S1, this is point A, this is point B, and now I've read in a new point C. Alright, so now we have A, B, C, we have 3 points. And in this case, the range AB, let's write it this way, the range BC, happens to be exactly equal to the range AB. Alright, so this is a case 1. And in a case 1, I have a closed loop, and the closed loop is of range AB. Alright, now we need to see what we need to do next. We have point A, point B, and point C. Well, it's kind of like this thing never happened. So when we have a case 2, we need to keep our point B or our point C as the middle point. We have 1 point stored, so we're going to need to use that one, and then we're going to have to read a new point C. So our point A is going to be equal to the last stored memory point. Point B, well, it's going to stay, well, I guess it's going to be point C now that we have here. And then we're going to read a new point C. Okay, so this one's going to be remapped back to A. This one's going to be remapped to B, and then we're going to read in our new point C. Well, let's see what we have now. We have 500 to minus 200 to positive 200. We have the range of BC is less than the range from AB. we have a case 3 again, no closed loop. Okay, so what do we do with case 3? Well, I guess here, since we took one away from memory, we need to have a subtraction here. So memory is going to be equal to memory minus 1. Alright, so now we don't have anything stored, but now we need to do this process again. We're going to have memory equal to memory plus 1. We're going to store point A in our first memory point. Point B becomes our new point A. This is our new point B, and then we're going to read in a new point C. So A is equal to the old B. The new B is equal to the old C. We're going to read in a new C. Okay, so this is the exact same thing that we did here. So as we see commonalities, we can group them together in our algorithm. We're going to do these exact same things time after time when we encounter these particular cases. Now there's a couple things we do have to watch out for, and I'll try to point those out as we look at these different examples. Alright. So now we look at minus 200 to 200 to 50. So again, we have a range BC that is less than range AB. We have identified another case 3, 2 consecutive case 3s. What do we do when we have that? Well, we're going to add a memory point. So memory is equal to memory plus 1. And right now that brings us to 2. We're going to store our point A. So that means this one is going to be S2, where S is a storage matrix. This is going to be our new point A. It's going to be our new point B. And then we're going to read in a new point C. Alright. So I'm going to need a little bit of room to finish this up. So let me save this page, and I'll make a little bit of room, and we can continue on with our algorithm. Okay, so I cleaned this up a little bit already. Now, let's see where we're at. This point is stored at position 1 in our array. This point is stored in position 2. We processed these 2 points, so we no longer have them. We don't have to worry about them at all. But now this is our A, this is our B, and this is our C. So what we have here is the range BC is greater than the range from A to B. Now this will give us a case 2. That means that I know that I have a closed loop that is of range AB. Let's see what those numbers are. So this would be a range of 250. That's this one right here. Previously we calculated this one has a closed loop range from minus 100 to minus 200 back to minus 100, has a range of 100. Right now, when we encounter a case 2, let's see what has to happen here. We get rid of A and B. Point C remains the same. If memory is greater than or equal to 2, what we need to do is we need to keep point C as it is. We get rid of point A and we get rid of point B. Our new point B will be our stored memory point 2. Our new point A will be stored memory point 1. So point A will be equal to storage mem minus 1. Our new point B will be storage of our current memory count. And point C just stays the same. Point C is whatever point C was. And now we go through our loop again. Now this is point A, this is point B, and this is point C. And here we have, let's do it this way, the range from B to C is going to be exactly equal to the range from A to B. We have a case 1. We have a closed loop from A to B. In this case, the range would be 500 to minus 200 to 500. That would be a range of 700. Okay, this big overall loop. And in this case, we are done processing. There are no points left. And our memory is reduced to 0. I guess we need a statement in here that says memory is equal to memory minus 2. And once there are no points left, and if the memory is equal to 0, then done. Now if we only have 1 point stored in memory, then our algorithm is a little bit different when we get a case 2. And that way our point A will be our stored memory point 1. Our point B will be the point, and then we'll read in a new C. Okay, so again, think about this algorithm a little bit, and we're going to take this, we're going to do another example. Then we'll formalize this, and I'll show you some Fortran code probably in a separate video. Well, on second thought, I think maybe this one example is probably good enough to get the main ideas across with this algorithm. Again, I want my students to develop this and to kind of work out the details on their own. We'll take a look in the next video about the details of the Fortran code that I've written that will kind of show this kind of algorithm. So if this makes sense, I think you'll be in good shape to understand that algorithm. The important thing to remember about this 3-point algorithm is that you do not read a new point every time you pass through this analysis branch. The case 1, 2, or 3 decision tree does not always result in the reading of a new point C. Sometimes you read a point C, sometimes you don't. And your point A, sometimes it goes in and out of storage multiple times, depending on the nature of the time history. So this memory can be increased or decreased kind of dynamically. If you're using a computer language like Fortran, which requires a fixed Fortran array size, depending on the version of Fortran that you're using, then what you can do is you can set a large number of memory points available for your array, and you can put in a check to make sure that you have not exceeded it. Alright, so I think with that I'm going to stop this video, and I will pull up my Fortran code and we'll kind of take a look through that. And I think you'll see a lot of things that are very similar to what we just talked about, and I'll point out some things that are maybe a little bit different if necessary.